Constantly asks how things actually work, well, you are in exactly the right place. Today, we're not just throwing around buzzwords about renewable energy. Oh no, we are popping the hood. We're going to explore the hidden physics, the intricate aerodynamics, and the complex engineering that makes massive wind and solar power plants actually function efficiently. We'll be using some fantastic source materials today to break down these huge concepts into structured, bite-sized pieces. Okay, let's dive into this. Consider this explainer your very own high-level engineering masterclass. We're using an actual syllabus for a course on renewable energy power plants as our inspiration today, and we're going to distill weeks of complex academic material into just the next few minutes. By the end of this, I promise you're going to look at the wind and the sun not just as weather, but as massive mathematical fuel sources just waiting to be captured. So, here's our roadmap for today. Section 1, renewable energy power plants. Section 2, the mechanics of wind. Section 3, optimizing wind generators. And finally, Section 4, mastering solar thermal power. Let's get right into it. Starting off with Section 1, renewable energy power plants. To really kick things off, we have to understand the sheer mind-blowing scale of what we're dealing with. Why are engineers so incredibly obsessed with optimizing these giant power plants? Well, it's because the potential energy surrounding us is staggering, and capturing it efficiently is absolutely crucial to moving away from fossil fuels. Just look at this number, 1.6 times 10 to the 7th power megawatts. That is the estimated kinetic energy available in the winds blowing across the surface of the Earth right now. To put that into perspective, that single number is practically equal to our entire present-day global energy consumption. The power is right there, literally blowing right past us. So the challenge isn't creating the energy. The challenge is physically and mathematically capturing it. Moving right along to Section 2, the mechanics of wind. So how do we build a machine that successfully reaches out and grabs all that incredible kinetic energy? The answer is actually up in the sky. Specifically, it's the exact same aerodynamic principles that allow massive airplanes to fly. We're dealing with two competing forces here, lift and drag. Wind turbine blades are shaped exactly like airplane wings. This relies on what engineers call the longer path theory. You see, because the upper surface of that curved blade is physically longer than the flat bottom, the air molecules traveling over the top have to move faster to reach the back edge at the exact same time as the molecules moving underneath. And thanks to Bernoulli's equation, we know that faster moving air creates lower pressure. This pressure difference literally pulls the blade forward. That perpendicular pulling force is called lift, and it is vastly more powerful than drag, which is really just the wind pushing flat against the blade. Lift is what effortlessly spins a massive turbine. Which brings us to the really important question. How do we maximize this mechanical force? Getting the blade to spin is one thing, right? But getting it to spin with enough force to generate grid-level electricity requires a deep, deep understanding of kinetic energy equations. The energy in the wind is proportional to the cube of the wind's velocity. Let that sink in. That means if the wind speed simply doubles, the power potential goes up 8 times. Because of that crazy cubic relationship, finding the absolute perfect wind speed is critical. Engineers have found the sweet spot to be exactly 15 meters per second. Why this specific number? Well, if the wind is too slow, like below 5 meters per second, you'd need absurdly massive rotors to catch enough air. But if it's too fast, say over 25 meters per second, the physical stress is catastrophic, and your million-dollar turbine essentially turns into a giant, dangerous metal frisbee. So 15 meters per second is that ideal Goldilocks velocity where maximum power output perfectly meets structural safety. All right, let's jump to Section 3, optimizing wind generators. Now, capturing the wind's rotational energy with those perfectly angled blades is honestly only half the battle. We also have to convert that spinning shaft into actual, usable electrical energy that can power your home. Inside a lot of these turbines is something called a wound rotor induction generator, or a WRIG. For years, the conventional way to control the speed was kind of clunky. Basically, they just burned off excess power as heat, which obviously resulted in terrible efficiency. But researchers came up with a massive game changer: combined input voltage and slip power control. Instead of just wasting that energy, this brilliant system dynamically adjusts the incoming voltage and the slip power simultaneously. It beautifully matches the generator's maximum torque with the wind's optimum torque. The result? The generator runs at peak efficiency across a huge range of changing wind speeds. Now, what's really interesting about this simulation here is seeing the theory actually put to the test digitally. Engineers built this incredibly complex virtual MATLAB circuit from their research data to prove that by combining voltage and slip control, they could successfully stabilize the variable wind energy. Not only that, but they could feed smooth, highly efficient power directly into a simulated electrical grid. But hey, a digital simulation is only step one, right? To prove it works in the real world, engineers have to build it. And they did, creating this, a 1 kilowatt experimental testing rig. What you are looking at is the actual physical manifestation of those digital blocks. They mechanically coupled a wound rotor induction generator to a specialized drive and brake unit to simulate wild, fluctuating wind speeds right there in a lab environment. And guess what? The data from this very rig proved the simulation was totally right. The combined control method massively reduced wasted heat and significantly boosted both the power factor and the overall electrical efficiency.